All right, thank you for joining us for this third lecture. Again, this lecture series is on Brightspace. You can watch them at your own pace. You can even speed up the videos or slow them down or pause them. So, we're talking about Laplace transforms. In the first two videos, we made a lot of progress. A few more things we want to talk about, and I want to show you. I've got a running table of all the Laplace transforms that we've figured out so far. Let me scroll over. Here's an example of it. You'll be given this. You'll be given something like this on the final exam. By the way, our final exam has been announced. It's Thursday, April 13th. So it's a week from this coming Thursday. Sorry, I should say April 13th. From 10:15 to 12:15 in Blount Auditorium, which is in Annex Central. Okay, so let me know if you have any conflicts. Okay, so it's the 13th. All right, so in any case, you'll have a table like this on that exam. It'll actually be a longer table. It'll have a few more things in it, but this really has everything that we've figured out. It doesn't have t squared in it or t, but you can get that from t to the n, right? And it also has last time you might remember in the last video we figured out this. We found this formula that it's a way to convert the Laplace transform of a derivative to Laplace transform without a derivative. In fact, if you apply that function, we could apply that formula to y double prime, since y double prime is equal to y prime prime. So here's what I'm saying: the Laplace transform of y prime prime would be, using this formula here, s times the Laplace transform of just the first y prime minus y prime of 0. Okay, so this tells us that the Laplace transform, y prime prime is just y double prime, would equal s times the Laplace transform of y prime minus, sorry, not equals, but minus y prime of 0. And now I could apply this formula again to this to get rid of that, and I get Laplace transform of y double prime would be s times, in parentheses, s Laplace transform of y minus y of 0 minus y prime of 0. If I distribute that s across the sum, I get s squared Laplace transform of y minus s times y of 0 minus y prime of 0 for the Laplace transform of the second derivative. Well, that's the formula that's in this table right here. Okay, so that's where that comes from. So now you've got both. You could even continue, and you could make a formula for the third derivative of y. I think we're only going to need the first two. So let me clean up some of this stuff so it looks a little nicer again. Just showing you where that came from. Okay, so good. One more skill I should show you. We need to practice. So we've got these two derivatives that we can make use of. Laplace transform of the derivative. Don't forget the properties also. The properties that the Laplace transform of k times f is k times the Laplace transform of f. And if I take the Laplace transform of f plus g, I could just do the Laplace transform of each one of them separately. Those are the same properties we have for integration. All right, with all these tools, hopefully we can avoid actually having to do an actual integral to compute anything, unless you're asked specifically to do it. There's a worksheet up, by the way, worksheet 16. It's on Brightspace, and that'll give you some practice doing these. There is one on there where it does ask you to compute the Laplace transform of a function using the definition, so you'll have to try it at least once, but it's an easy one. What is the definition? Let's put that up here. The definition of Laplace transform Hopefully you remember this. It's the integral from 0 to infinity e to the minus st f of t dt. That's an improper integral, so it only converges for certain values of s. We should have added this to this table. This is for s greater than 0. Same thing, s greater than 0. This is for s greater than a. And the rest, I think, are all true for s greater than 0. Why do we have to say what s is? Well, technically, that definition I just showed you doesn't converge for all s's. Okay, so the truth is you don't... For our techniques that we're going to learn, we don't really care that much about what s is, but I just want to be complete. Okay, so one more skill we should try. So by the way, this worksheet I think it's due Thursday, but really you can do it anytime this week. And by the way, I should say there'll be an online exam available for, this will be a replacement for exam number 4. You can take it at your leisure. It'll be available Wednesday morning until the following Tuesday. So it'll be available Wednesday 4/5 until Tuesday, the end of the day, Tuesday, which is the last day of classes, by the way, 4/10. Sorry, not 4/10, 4/11. Okay, so you'll have a full week, beginning of Wednesday to the end of Tuesday. All right, and then of course the final will be a week from Thursday, the 13th. All right, so another skill that we need, and then we can really start solving differential equations. I referred to this at the end of the last video. We need to be able to undo a Laplace transform. In other words, if someone gives you the Laplace transform, you have to be able to find f. You could think of this as an inverse Laplace transform. So it's sort of like L inverse. Here's an example. Suppose the Laplace transform of some function that you don't know, some function of t, happens to equal something like 7 over s plus 6 over s plus 2, and then minus 3 over s squared plus 25. And then I might say, find the original function f of t. In other words, what function would have this Laplace transform? So in other words, find f so that if I took its Laplace transform of f, I would get that. Okay, so we're doing Laplace transform in reverse. All right, so this is a skill we need to be able to solve things. So solution. Well, the nice thing is that just like the original Laplace transform splits up over addition, so does the inverse. So we have to invert 7 over s, 6 over s plus 2, and 3 over s squared plus 25. We can just work on each of those separately and then add them together or subtract them in the case of the last one, right? So, all right. So in fact, also, because of the 7 over s, we could also pull the 7 out. So what's the, what function's Laplace transform is equal to 7 over s? That one should be a pretty easy one. Let me zoom out and go to our table. Scroll over here. Hope you remember some of them. 1 over s is the Laplace transform of just 1. So I think we had 7 over s, right? So the Laplace transform of 7 will be 7 over s. Okay, so let's go back. Sorry for all the scrolling. I'll try not to go too fast so it doesn't hurt your eyes or anything. So this would just be 7. Just 7, right? The answer would be just 7. Because the Laplace transform of 7 would be 7 times the Laplace transform of 1, which is 1 over s. Okay, what about this function? All right, so if I scroll over that table, I'll do it slowly. You'll notice there is one entry. There's an entry, maybe I don't have to scroll over. There's an entry, it said e to the at for the f, and the Laplace transform of f, it was 1 over s minus a. So if you went back to that table, this is what you'd find for one of the entries. E to the at goes to 1 over s minus a. See how that looks similar to this? That's the entry you want to find, so we need to figure out what a is. Well, I think if you just look at it, you'll see a must be -2. Right? So the Laplace transform of e to the -2t would equal 1 over s minus a -2, which is s plus 2. How do I handle the 6? I have to put a 6 in front of it. And that's it. Okay, so I inverted this one to get 7. I inverted this one to get 6 over s plus... Sorry, I didn't get 7. That was the answer, right? The inverse is this function here. 6 e to the -2t is that piece. 7 is that piece. We still have to do this third piece. And then we'll add them all together. There's actually a negative in front of the 3, but we'll just throw that in at the end. So if you look on that table, I'll scroll over to it in a second. We're going to look for one that has a number on top, and on the bottom it has s squared plus a number. So I should say just a number on top, no s's. And on the bottom is s squared plus a number. Okay, so let me scroll over to the table, or you can... All right, so let's scroll over to this table. Let's look for that, something that looks like that. It looks like it's one of these two here. Which one is it? Well, it's going to be the one that has just a number on top. And so b is just a number, and s is the variable. So that's this one here. So it looks like it'll be sine of bt. It'll be sine of bt always produces b over s squared plus b squared. Okay, so that's the one. We're going to transfer this information over. Sine of bt goes to b over s squared plus b squared. Let me go back to our problem. You'll have this table on your test for your final. And of course, the online exam, test 4, that'll just be open note anyway. But so we saw that sine of b times t goes to the Laplace transform of that is b over s squared plus b squared. Okay, so what does b have to be here? We look at this term here, b squared, so it would be the square root of this. So here, b must be 5. So we're looking at the function sine of 5t. And sine of 5t, we know, goes to 5 over s squared plus 25. We have 3 on top, so how do we fix it? We're going to have to adjust it, right? What do we have to multiply 3 by? What do we have to multiply 5 by to make it 3? I think you're going to have to put a 3/5 next to it to kill off the 5 and leave it with a 3. So I need a 3/5 here. So that's the answer for the third piece. The Laplace transform of 3/5 sine of 5t, if you work it out, would be 3/5 times 5 over s squared plus 25, which would be 3 over s squared plus 25. And that's what we wanted. So that's the final piece. We have to combine them, right? So the answer would be f of t is, I add this piece, 7, plus this piece, 6e to the -2t, and I still have to add, actually I'm subtracting, so minus this last piece, 3/5 sine of 5t. And that's it. We found the function f. If we were to take its Laplace transform, we would end up with this. Okay, so we got it. We can now undo a Laplace transform. There's an example of it. Okay, so why do we need that skill? Here's why. Now let's solve some differential equations. They have to have initial conditions, by the way. Otherwise, you can't use Laplace transform. So these are called IVPs. Laplace transform only work when you have initial conditions. Okay, so here's an example. Let's solve this first one. Y prime minus y equals 3 with, let's give an initial condition of y of 0 equals 7. If we didn't have that initial condition, we wouldn't be able to do it. By the way, this is a problem you could do using an older technique in our class. This is I think you could do an integrating factor here, and it would work, or you could do a linear and because it's non-homogeneous, you could guess at a solution, yp, you do yc plus yp. That you might, hopefully you remember that. You're gonna have to do that in the final, but we're not going to do it that way. We're going to use Laplace transforms. And there's always 3 steps when you do this. 1, you take the Laplace transform of both sides of the equation. Second step, by rearranging, solve for Laplace transform of y. Get it by itself. And then the third step is undo the Laplace transform using we just had an example of that, by using the table in reverse and splitting things up to get y of t equals to something. That's our goal, to solve any differential equation. Find the function that solves it. Okay, so we're going to do those 3 steps. Okay, so let's do it here. Here's the solution. Okay, so the Laplace transform of the left side, y prime minus y, equals the Laplace transform of the right side. Okay, so remember some of the properties. This will be the Laplace transform of y prime minus the Laplace transform of y. Just we can split up Laplace transform across addition. By the way, what is the Laplace transform of 3? Well, that would be 3 times the Laplace transform of 1. If you look up in the table, Laplace transform of 1, it's just 1 over s. To make it look like an s, I'll put these little marks on the end. Okay, so we've got 3s here. Sorry, 3 over s here. We still have to work on this. We don't like having derivatives in our Laplace transform. So we're going to make use, if you look at that table, this is y prime. If you look at the table, you scroll over there. You'll have this table in the exam. I'll scroll over there because that's in there, right? Laplace transform of y prime. It's way up here. Zoom in. It's right here. Zoom way in. So it's s times the Laplace transform of y minus y of 0. So sorry for all this scrolling, but let me zoom back. Just wanted you to see that it's there in the table. We're going to use that for this right here. We just looked that up, and it's s L of y minus y of 0. We still have this. This didn't go anywhere. I just replaced, this whole thing came from that. We still have this equals 3 over s. Okay, so we accomplished step 1. That was step 1. Step 2 says use that expression to solve for Laplace transform of y. But actually, I should have said, and substitute. We might as well do that now. Any initial conditions. So in other words, do we know what y of 0 is? We do, because it was given to us in the problem. It was given to us that y of 0 is 7. So I've got s L of y minus 7 minus L of y equals 3 over s. All right, and I want to solve this. I want to get L of y by itself. Solve for it. Okay. So this is just an algebra skill. Here's the trick. When you have a bunch of terms a bunch of things in a bunch of different terms in an equation. You want to solve for one specific thing. Get all terms that have an L of y in them on one side of the equation. It looks like we're going to get them on the left side since they're already mostly there. And all other terms that don't have an L of y in it on the other side. So for example, I want to bring that 7 to the right side by adding it. So if I do that, I think you'll agree I get s L of y minus L of y equals 3 over s plus 7. We're almost there. Then, what's the next step? Then factor it out. Factor out L of y if it's in more than one term anyway, which it is here. So I factor in L of y here. What do I have left inside? Remember, this is an S, not a 5. I'm just making it look like an S with the funny font. What's left inside here? This is also an S. Sorry about that. So if I factor out an S, let me just writing here. Pen stopped acting. Let's see here. Give me a second. Okay, so what's left if I factor out L of y from both of these terms? Well, there's an S left in the first term. And what about the second term? A 1. Because that's the only thing in that term. So now I have to divide both sides by s plus 1. Although I should write the right-hand side a little nicer. We don't like to have fractions inside fractions. So we'll think of it as multiplying by 1 over s plus 1 and distributing. It's the same thing. These cancel, and I'm left with L of y equals 3 over s times s plus 1 plus 7 over s plus 1. Sorry, you know what? I think I made a mistake. Yeah, I hope somebody saw this. I know it's a video, so you can't say anything. I forgot. This was a minus here, so I apologize. Let me use red to fix what I had. This should have been minus, which means this should have been minus, and this should have been minus. And so is this. So let me correct all this down here. This should be s minus 1, and this should also be s minus 1. Okay, so in other words, what I really should have had, I just made a little error. It should be L of y equals 3 over s times, in parentheses, s minus 1. Those are s's, not 5s. Plus 7 over s minus 1. Yeah, that's better. So we finished step 2. We solved for L of y. We're almost done with the problem. All we have to do is figure out what function has this as its Laplace transform, and that'll be the function y that solves the differential equation. So for the third step, we need to do the Laplace transform in reverse, right? So we have to figure out what function has those as its Laplace transform. Okay, so it turns out, so we have to do both pieces. So it turns out this one here is easy. That's easy. It's easy to find this one. What function will produce that as its Laplace transform? Remember, it's that one f and L of f. It's that one that said if you have e to the at, you get 1 over s minus a. So it should be obvious here that a would be 1. This would be a. So the function is e to the 1 times t, and the only difference is because of the 7 on top, I have to put a 7 in front of it. So it'll be 7e to the t, right? So this one here will come from 7e to the t. I just have to do the inverse Laplace transform of this. Let's think about this. Well, it turns out if you go back on your own and look at that table, you'll see that there is nothing like this in the table. If you distribute that s through, you get an s squared, and you might think it's the sine or the cosine, but it's not, because it's always s squared plus a number, and this would be s squared minus an s, so it's not the sine or cosine. The 3 is not the problem. We can pull that out. The problem is the denominator. So here's what we have to do. we want to, it'll be easier if we split this up. We need to do the following decomposition. We need to find a way to write 3 over s times s minus 1 as something over s plus something over s minus 1. How do I know I can do that? Well, think about, suppose you were adding these two fractions together. How would you do it? You'd find common denominator. The common denominator would be s times s minus 1, and then you would add them together. So we're basically doing common denominators in reverse. We're adding a fraction in reverse, and it has a name. It's called partial fractions, because this first one is a fraction of just the first part, and the second one is a fraction of just the second part. So it's called partial fractions. So we have to figure out what these question marks are so that these are equal. So here's the technique. What you do is, we don't like to use question marks in math equations, so we'll call the top number A in the first fraction. The top of the second fraction, we'll call it B. Should be S's here, right? And basically we want to solve for whatever A and B have to be that make those two expressions equal. And not only do they have to be equal, they have to be equal for all values of s. Okay, so anytime you're trying to solve an equation that has fractions in it, you do something called clear fractions. How do you clear fractions? You multiply both sides by the greatest common, or I should say the least common denominator. All right, well in that case, I'm going to multiply both sides by s, and also by s minus 1. Okay, so when you do that, on the left side, all the s and s minus 1s cancel, and what you're left with will be 3. On the right side, you'll put an s and an s minus 1 on both of these. And here the s's cancel. Here the s minus 1s cancel. So you're left with a times s minus 1 plus b times s. And you're trying to solve for a and b. You might recognize this is kind of similar to when we did our guess for yp, and you had a, sometimes you had a or as plus b and things like that, or at squared and all that stuff, and you had to try to figure out a, b, and c. You're kind of doing something similar here. There's actually a shortcut here. Since this has to be true for all s, you can choose values of s to make things simple. There's really infinitely many equations here for every possible value of s. For example, I could choose, if s equaled 10, then this equation says 3 equals 9a plus 10b, right? Because if I replace s with 10, that's what I would get. So you could keep doing that and get a system of equations to solve for a and b. There's nothing wrong with that. But it's something better. Suppose I chose s equals 1, for example. Plug in s equals 1 into this expression and see what you get. Well, you get 3 equals a times 1 minus 1 plus b times 1. Of course, 1 minus 1 is just 0. So a times 0 is 0, and you're just left with 3 equals b. So we solved for, you can only do this because these are an s in this equation. You know, most equations don't have an s. So we got b pretty easily without having to solve a system of equations. What about, is there something I could plug in for s that will enable me to have an equation that just has a in it? Yeah, if I let s equal 0, then we get, the left is 3, the right will be a times 0 minus 1 plus b times 0. So the b term is now gone, and I've got 3 equals, this is negative 1, negative a. So a would be negative 3. So I got my a and my b in my partial fraction decomposition. So all of that work was just so that we could say 3 over s times s minus 1 is equal to negative 3 over s plus positive 3 over s minus 1. If you're not sure if that's right, you could just use common denominators to add these together and make sure you get back to that. You will. All right, so why is that nice? So that if I have to do the inverse Laplace transform of 3 over s times s minus 1, instead I can just do the inverse Laplace transform of minus 3 over s, and add to that the inverse Laplace transform of 3 over s minus 1. Well, this one's nice. This is just negative 3 because the Laplace transform of 1 is just 1 over s. And this is that e thing again. This will be 3e to the 1t. Just add them together because they're being added here. So that's the Laplace transform of this, the inverse Laplace transform of this function here. If I were to find the Laplace transform of this, I would get the inside part, 3 over s times s minus 1. Actually, I would get this, and then if I added them together with common denominator, I'd get this. So remember, that was just part of it, though. The other part of it was, zoom out here. This was just this piece right here. We can add to it this piece. So overall, y of t would equal negative 3 plus 3e to the t. That's what we get from this piece. And then we have to add to that plus what we got from this piece, the one that we said was easy and we did first. That was 7e to the t. This is our final answer. Now, these are like terms. We should add them together. So we get negative 3 plus 10e to the t. That's our solution to the differential equation. By the way, if I wanted to check it, I could just check it by taking its derivative and plugging it into the differential equation that we started with, which is way up here. It was this problem right here, y prime. Right, we could check it by checking it if we wanted to. We plug that y into the original differential equation, which was y prime minus y equals 3. You'd have to take the derivative of this, and then also plug that in here, and then also get y itself and plug it in there and see if it equals 3. It does. You can try that on your own. It's not too hard. Okay, and you'd also have to, by the way, you'd also have to check that the initial condition is also true. Is y of 0 equal to 7? If you plug in 0 for t, you get minus 3 plus 10, which does equal 7. So that even that one checks. So you'd have to check both, really. Okay, so that's it. That's how we solve. We did all 3 steps. We ended up with a function of y. We did these 3 steps here. You take the Laplace transform, solve for L of y, and then undo the Laplace transform. It's kind of a cool technique. Now, one thing I should mention, unlike the old methods, we can't get a general solution. So there's never going to be a C1 or C2 in this, like you sometimes get. Because, why? Because we already replaced we used our initial conditions. So in the old technique, we would use our initial conditions at the end of the problem to find C1 and C2. But in this technique, we replaced y of 0 early on. If you remember, this y of this initial value got replaced in the middle of the problem. So if I change my initial condition, I can't just wait till the end. I have to use it early on. I would have to sort of redo the problem. So that's one thing to keep in mind. You can only use Laplace transforms to get explicit solutions and not general solutions. Here's one solution. All right, let's do one more problem, and then that'll be the end of this video. All right, so let's do another example. This will also give us another chance to practice our partial fraction decomposition. That's really the only kind of tricky thing, I think. So let's solve this one. Use Laplace transforms. So I don't want you to do it the old way. To solve y double prime plus 2y prime equals 0 with initial conditions y of 0 equals, y of 0 equals 1 and y prime of 0 equals 7. Notice we need 2 initial conditions here because this is second order. 2 derivatives, right? So we need 2 initial conditions, one for y and one for y prime. Of course, we could do this the old way. It's linear, homogeneous, but let's use Laplace transform. It'll be just another example. Okay, so remember step 1. Step 1 is to take the Laplace transform of both sides. So we have the Laplace transform of y double prime plus 2y prime equals Laplace transform of 0. Okay, well, Laplace transform of 0 is just 0. I don't even think that one's in the table, but it would just be the integral of e to the minus st times 0 dt, which is of course 0. The integral of 0 is just 0. Alright, so what about the left side? Well, that's the Laplace transform of y double prime plus 2 times the Laplace transform of y prime. What do we do now? If you remember the table, I'll write, instead of scrolling over, let me just tell you what these are again. In the table, we did this at the bottom of the table. We discovered that the Laplace transform of y prime is Laplace transform of y times an s in front of it minus y of 0. And the Laplace transform of y double prime is s squared times the Laplace transform of y minus s times y of 0 minus y prime of 0. Those are the two equations that we need. Since this is second order, we need the second one as well as the first one. This one will replace that one, and this one will replace that one. So we get. So let's do this. We get this s squared L of y minus s times y of 0 minus y prime of 0. That all came from this. We still have this plus 2 times, in parentheses, this here, s L of y minus y of 0. And that will all equal the right-hand side, which is still 0. Now is a good time to plug in our initial conditions. Right. We could scroll back up to see what those were. That's here. So y of 0 is 1 and y prime of 0 is 7. Okay, so y of 0 is 1 and y prime of 0 is 7. I'm going to go back to this. So this is 1, this is 7, and this is 1. Those are the only places where I saw them. And that'll be different in different problems. Those numbers might be different. You just have to look at the initial conditions given to you. But so what we'll get s L of y minus s minus 7 plus 2s L of y. I'm distributing this 2 here. Minus 2 equals 0. Might as well add some like terms here. You see the minus 7 and the minus 2 will add up to negative 9. I don't think this negative s adds up to anything. Remember the trick. We're trying to solve for L of y. We need to get L of y by itself so we can do step 3, which is to do the reverse. So I'm going to want to bring this term and this term and this term all to the right. So we get s. Sorry, I think this was an s squared. I lost an s squared, didn't I? Hopefully you caught that when I was doing it. I'll use red again to fix my mistake. There should have been an s squared here, so it should be here. Sorry about that. It should be an s squared there. I think that's the only mistake I made. I think I was too focused on putting these little edges on the s to make it look like it's not a 5, but it should be s squared. Right, so let me go back to blue. S squared L of y plus 2s L of y. That's these two terms. And all the other terms should be on the right. So equals s plus 9. The 2 and the 7 add up to 9. And so now I factor it out, and I get L of y is equal to s squared plus 2. Sorry, not equal to. I factored it out. I shouldn't have an equal there. Times s squared plus 2. I just factored it out. Equals s plus 9. So now I just have to divide, right? So I can get L of y equals to s plus 9 over s squared plus 2. Okay, so, okay, that's not too bad. I did that right. Oh, you know what? I did make a mistake. I apologize. I factored this out. I left out a 2. Not the 2. I left out this s. There should be an s here. So my apologies. There should be an extra s here. Okay, but I fixed it. That's all. That's all I had to do. I forgot about this 2s. I thought it was just 2. It's too bad, because if it was just s squared plus 2, we could actually invert it pretty quickly just using sine and cosine. Okay, so we're almost there. We need to do step 3 now. We need to undo this. We need to undo the Laplace transform. In other words, we have to find y, which function y has this as its Laplace transform. Find y of t. And that'll be our answer. All right, so it turns out we could write this, by the way, s plus 9. We could factor an s out of the bottom here, and we get s times s plus 2. Those are the same. If I factor an s out of both of these two terms, I get this. It's the same idea before. We can't invert this. If you look up in the table, you won't find it. You want to write this as something over s plus something over s plus 2. So we'll do the same trick. I'll do this one a little faster just because it's kind of a repeat of the last time. It's just the numbers are different. So I'll call this one A and this one B. By the way, the rules here, usually it's just A and B on top. Once in a while, you might have to do, like if the denominator was something like s squared, it's something that doesn't factor. If the denominator was something, maybe a quadratic, like s squared plus s plus 1, then on the top I'd have to do as plus b, and then this would be c. Okay, but I'll try to keep those more complicated examples of partial fractions off. I don't think we give you those on the test. We try to keep it straightforward, like this one right here, just an A and a B. It's a little bit easier. Okay, so I have to figure out this decomposition so I can undo the Laplace transform. Once I get it to this would be easy to undo, because this will just be A, and this will also be undo with an exponential e to the, e to whatever s minus a is, whatever a is for this to be s minus a. So it's the same thing. We clear fractions by multiplying both sides by s and s plus 2, and we get, on the left side, we were left with s plus 9 equals, on the right side, we'll have, the s's cancel here, and I get s plus a times s plus 2. And for the b term, the s plus 2's cancel, and I'm left with b times s. Okay, so I'm almost there. Remember, this has to be true for all s. So I could just choose any value of s and start creating equations for a and b. Well, let's choose some nice ones. If I choose s to equal -2, I hope you agree, it'll kill off the a, because you have -2 plus 2 there, and we'll get, the left-hand side will be what? It'll be -2 plus 9, so it'll be 7 equals -2b. So what's b? It's easy. Just divide by -2 and get 7. So -7 over 2. -7 halves, so -3.5. And how do we get a? What would be a good choice for s to get a by itself? Well, if I let s equal 0, it'll kill off the b time, because it would be b times 0. And I'm left with 9 equals 2a. Because this just becomes 2 when s is 0. And so a is equal to 9 over 2. So I did it. I accomplished it. Those are the two question marks. A is 9 over 2. B is -7 over 2. Let me scroll back here. So I can, this is going to be 9 over 2. And this was -7 over 2. I think I got that right. Yep. So, in other words, we're almost done. To get y, we have to now do the inverse Laplace transform. So y of t will be the inverse Laplace transform of those two expressions, 9 over 2 over s minus 7 over 2 over s plus 2. Well, this one is just 9 over 2, because remember the Laplace transform of 1 is just 1 over s. So the Laplace transform of 9 over 2 will be 9 over 2 over s. And then what about this one? This is that exponential. Remember the Laplace transform of e to the at is 1 over s minus a. So think about what a would have to equal here to get the bottom to be s plus 2. I think you'll agree that a must be negative 2. So it'll be e to the negative 2t, but then because I have a minus 7 halves on top, it'll be minus 7 over 2 e to the negative 2t. So it was much easier to undo the Laplace transform for these two things separately and subtract them. That's why we did partial fractions. And this is our final answer for that differential equation. This is the function that solves it. You could check it by taking its derivative and plugging it in. Notice there's no c's in here. It's not a general solution. So, of course, there's no s's in here because we undid the Laplace transform and got back to a function of t. Okay, so that's it. Okay, so you can practice these. There's a worksheet 16. There's one more, major topic in the next video, and it's how do we handle step functions, functions that suddenly turn on or off. So like off and then on. We're going to learn how to handle those types of functions in differential equations, and that's really what Laplace transforms are useful for. All right, I'll see you in the last video.